So we're talking about electrophilic addition reactions. Of carbon-carbon double bonds and carbon-carbon triple bonds. And the key fact, right, that kind of governs all of these is that the pi bond is a nucleophile. So every mechanism that you're going to be working with in this chapter is going to start with an arrow coming from the pi bond and attacking something. So if we look at propyne as an example, what we're looking for is an electrophile, right, that's going to get attacked by that pi bond. Right? In general, nucleophiles don't attack the pi bond because the pi bond is electron rich. So there are a lot of reactions, and keeping track of the reactions can be difficult, but there are kind of two fundamentally different mechanisms. Depending on what the electrophile is. Right. If the electrophile is hydrogen, usually in the form of hydronium ion, right, then there are discrete carbocation intermediates, which are then subject to rearrangement and all the other reactions that carbocation intermediates undergo. If the electrophile has a pair of electrons on it as well, as a partial positive, then there's a concerted ring intermediate. Right, concerted reaction. So the lone pair of electrons is going to attack one end of the pi bond at the same time as the pi bond is attacking things. And it's often a three-membered ring. So you'll see a lot of different electrophiles, but there's going to be a tendency for those electrophiles to all go through the same three-membered ring. So what do I mean? What I mean is if you've got something like iodine monochloride, for example, right? It's a heteronuclear diatomic. There's going to be a partial positive charge on the less electronegative iodine and a partial negative charge on the more electronegative chlorine. So the electrophile is the I, but it also has pairs of electrons. So the pi bond is going to attack the iodine, but at the same time, one of these pairs of electrons is going to come in and attack the other carbon. And I want to draw the pair of electrons pointing at this carbon. That's the more substituted carbon, which means it has a larger delta plus in the transition state. So I'm going to go through an intermediate that has partial bonds to both carbons, to the iodine, and I'm also going to kick off chlorine. So you can think of this part as being kind of an SN2 reaction at iodine, where the chloride is the leaving group, Cl minus. But then we've also got a three-membered ring transition state. So my transition state is going to look something like this. The pi bond is partially broken. I've got partial bonds between both carbons and the iodine, and I've also got a partial bond here where that bond to chlorine is breaking. There's a partial negative on there, and there's a partial positive, and I'm drawing it in the middle of the ring because that partial positive charge is distributed on both carbons and on the iodine. And then when the smoke clears, you'll have what's called an iodonium ion in this case. Now the formal charge is just on the iodine, and you'll have chloride being given off. So this is an iodonium ion. And in terms of reactivity, that iodonium ion looks identical to the protonated epoxide, right? If you work with the epoxide under acidic conditions, we have a 3-membered ring intermediate that's got a protonated epoxide. So if you know how this is going to react, you also know how this is going to react. Because the nucleophile that's going to come in and attack doesn't really care what this piece looks like. It's just going to see a larger partial positive charge on the more substituted carbon and a smaller partial positive charge on the less substituted carbon. So the chloride ion is going to attack that carbon, pushing out a pair of electrons. This is an SN1-like mechanism. It's stereospecific, but it happens at the more substituted carbon because of the larger partial positive charge. Just as it would for the protonated epoxide, it works the same way on the iodine. So when we're done with this iodine molecule, we have added iodine to one side of the double bond and chlorine to the other side of the double bond, and it is a stereospecific anti-addition. Here you can't tell it's an anti-addition because we've got an acyclic molecule, but if you had a cyclic molecule so that you were tied together, you would find that the anti-addition would give you the trans product. So the chlorine and the iodine have to be on opposite sides of the ring. And there are a lot of substances that will undergo that same type of reaction with the 3-membered ring. All right, so cyanogen bromide, BRCN, that has a resonance structure that has the double bond to the bromine, which puts a positive formal charge on the bromine, which means there's a significant delta plus on bromine, so bromine is the electrophile there. Sulfur and selenium chloride bonds will do the same thing. Chlorine is more electronegative than sulfur, so delta plus on sulfur, delta minus, and you'll notice in both these cases, in addition to the partial positive, there's also a lone pair. That's the key feature that tells you that you're going to go through one of these 3-membered ring intermediates. So anytime your electrophilic atom has both a partial positive charge on it and a lone pair, 3-membered ring intermediate is going to be what you're seeing, and you should be on the lookout for those. Right? There are other electrophiles that have this same kind of feature. Another one of those, it looks unrelated initially, would be a carbene. So you'll see a molecule like this, where we have an unfilled octet, right, which means that it's electrophilic, but we also have a lone pair, which means it's nucleophilic. This carbene, this methylene carbene, will add to that pi bond. The pi bond will attack the empty p orbital, but at the same time that lone pair of electrons will attack the partially positive carbon, and we will end up making a cyclopropane ring out of this. It's a similar 3-membered ring transition state to what you see with those other electrophiles. Right? So the pi bond attacks an empty p, but the lone pair in the sp2 hybrid orbital attacks the partially positive carbon. It doesn't look like the same reaction, right? Reacting with this methylene carbene to form a cyclopropane ring doesn't really look like the same reaction as reacting the double bond with ICl, but it's the same principle, where you have an atom that is simultaneously nucleophilic because of a lone pair and electrophilic because of a partial positive or an unfilled octet. So that's it, I think. Don't think I want to keep you any longer. We got 15 more minutes. If there are questions, though, and I'd be happy to answer any questions that you might have on what you're going to be looking for in the videos that you're watching on the alkenes. And I think I put in the chat on Discord already what videos you should be watching for what days to kind of stay on track. You could, of course, wait and watch them all over the weekend, since Thursday's quiz won't have anything to do with reactions. So that's your call, depending on what else you have